right, so 17th lecture. 17th lecture, only a few more to go. We're nearing the end of the semesters, which is semesters. We're nearing the end of the semester, which is great. But we have a lot more to cover. So today we are gonna go over, finish up our discussion of convolutional neural networks. There's just a few things that I didn't get to last time that I want to still cover. Then we'll have a discussion of important machine learning models, and then we'll have a discussion of recurrent machine learning models, and then we'll go back to some machine learning basics for the next 3 lectures starting Thursday. So, one thing that we didn't get a chance to do is, with convolutional neural networks, is simply the idea of blocks of modules. So with convolutional neural networks, I think that's better. Let's do that. With convolutional neural networks, we had multiple layers, multiple convolutional nets, multiple filters, one after the other, and then we defined that all in a torch.nn class. But we can abstract this creation a bit more using the nn.sequential class. So the nn.sequential class just allows us to bundle collections of layers together that will be called sequentially. So it's pretty useful in the sense that you don't necessarily need to keep track of every single layer. So this becomes especially important when you have multiple layers operating in parallel. We haven't seen very much of that currently, but when you get to some of the more advanced models like AlexNet, like really anything you see in literature currently, you get this whole idea of multiple layers operating concurrently. And so when you have that, it just gets hard to keep track. So it's nice to organize things into blocks. So all the torch.sequential does, the nn.sequential does, is simply organize things into blocks. So for instance, in this convolutional neural network, which I believe we explored last time also. Actually, no, this is a bit more complex than the one we explored last time. We have a 2D convolution. We have a number of in channels, number of out channels, kernel size, et cetera, padding, stride. We know what that means. Then we pass it to a ReLU activation function. Then we do another 2D convolution. We pass it to another activation function. Then we pass it to a max pool. Then to compress the number of features a bit. Then we have a second block and a third block that largely do the same thing, just with different parameters. Yeah, just with different parameters. For instance, we have in channels are 32 here instead of 16. We have to match the out channels here to the in channels here. That's why we do that. So we have these 3 blocks, and what's nice is that when we define our forward function, we could simply define the forward function by using each one of the blocks instead of by calling each one of the different layers. Okay, so it shortens things up. To a certain degree. What's very useful also is that, for instance, if you wanted the 2 blocks to operate parallelly, for instance, if you wanted if you wanted 2 of block 1 to operate parallelly, you would simply say x1 equals block 1, and then something like x2 equals block 1 times x, and then block 2, you would pass in, I don't know, you would pass in x1, comma, x2, right? So that sort of thing. It just allows you to do that sort of thing very easily. That's the only reason that I'm bringing this up, because you will see it, and it makes your life substantially easier in many cases. Especially when defining the forward function. I think that's all I wanted to mention there. And this is, of course, just testing just printing the model. So remember, you can always print the model, and the print function is overloaded so that when you ask it to print the model, you get the actual layers that are needed, the actual layers in the model, and it lists them like layers 1, 2, 3, 4, 5. And then, of course, if you use sequential blocks, it'll organize it by the blocks as well. Yeah. Does that make sense? Very basic thing, but it is very useful when you need it. Yeah. Okay. So let's go back to fully convolutional networks. So last time when we discussed the convolutional networks, we had an input, and then we passed it through a bunch of convolutional filters, one convolutional layer after another convolutional layer after another convolutional layer, and they all connected together, and then they outputted a classification or something of that sort. So that is what's known as a fully convolutional network. Basically, all the weights fan in or fan out to each other. There's no weights that basically have no parallel blocks. You have no cases where things diverge and then come back together. That's all that fully term means. This is the same. This is pretty much analogous to fully connected networks. Basically, at every layer, all the weights from layer n-1 are connected to all the weights from layer n. Convolutional networks could be applied to many tasks beyond classification. And so one of the big tasks for instance, here is called image segmentation. Simply the idea that we want to basically break up an image into different categories, into different parts. So for instance, we have a picture of a street with some cars here, and we want to be able to identify the vehicles, and then we want to be able to identify the road, the sidewalk, the buildings, etc. Right? So what we do in this case, at least this is the first step to sort of image processing on a road, is simply that you want to know what parts of the pictures belong to what class. So there are a bunch of ways to do it. For instance, one way is for instance, there's a bunch of ways to do it, but the first sort of step is simply for every pixel to identify what class that pixel belongs to. All right? That's sort of what we do visually. We look at a picture, and we see that this is the road. We're looking at every single pixel, and we're like, okay, the road is all this stuff. And then we just basically color in the parts that are the road. So that's pretty easy. That's a task that we can do with a convolutional network. We could look at every pixel in the road and then categorize it as a road or a sidewalk or a building, etc. So what we could do in this case to accomplish this thing, we have to come to realize that the difference between what we need right now versus what we did last time is right now we're taking in an input, a whatever, n by m input, n by n image. And so last time we were just sort of classifying whether or not the image was a car or a letter or a cat or whatever, right? This time we're not just doing one of 8 categories. We're not just classifying the whole image based off one of 8 categories. We're classifying each pixel as one of 8 categories. So the input is an n by n image. So the output also needs to be the same size, the n by n image, right? The only difference is that whereas each pixel was some RGB value here, now each pixel is one of M classifications. So what do we do in this case? How should we construct our network? Well, we can't just do a straight fan in because we need to have the same amount of pixels at the output as we had at the input. So what we do is what's called a encoder-decoder structure. We do our normal convolutional network to sort of get features from the image, compress those features, fan in a bit, right? We don't necessarily want to make the network too large. We want to have some sort of compression. So same thing we do. So the encoder is simply there to sort of look at the input image, get all the features so that we could later use that information to get the output. Then we use what's called a decoder, which goes from the features, all the features you got from the encoder, and basically use those features to reconstruct the image or output into whatever manner you want. So in this picture right here, we have a encoder. We have this input. It goes into an encoder, which, again, is just a bunch of convolutional layers, same as we had before. You could use it as a block, but you could do it as a block, whatever. You have multiple convolutional layers. In between each convolutional layers, you have a nonlinear activation function. And then through this processing, you get to this point. So you get to the end of the encoder where you have some size vector that basically contains a bunch of values that represents some aspect of the image. It represents some aspect of the image. Doesn't necessarily need to be a one-to-one correspondence to the image. It could be the number of features at this point could be much larger than the image. It could be much smaller than the image. Who knows? But you get to this point where you have some set of values here. You have some set of values here, some matrix of values here. That's called the state of the network. That's the encoder output state. And then you have some set of values that represent the features of the image. You pass this into a decoder, which simply looks at the features from the input image and then simply wants to know, okay, I have those features from the input image. I want to reconstruct the image, except now, instead of reconstructing the image visually in terms of RGB values, I want to reconstruct the image where each pixel is a particular class. So so you do all of that, you pass it to the decoder, you do all that, and you get what's known as a segmented image. Basically, every pixel basically you break up the image so that every group of pixels represents a different type of object. So in the example again, you see a bunch of buildings, you see a road, you see a car, some cars, and the sky. So that's how image segmentation works. Basically, you have a encoder, which is the convolutional neural network that we discussed last time for the forward stage. We have an encoder, which is the convolutional neural network that we discussed last time, and then you have a decoder, which is basically the same thing. In fact, it could be a mirror image of the encoder. The only difference is that it's the same thing. The only difference is that you go from some amount of states to an output, to an n by n image. Okay. Yeah, does all that make sense? I forgot to mention. So So I don't think if the pooling layer so pooling layers aren't necessarily fully connected layer or not, right? So if you have mean pooling, then you have the weights that combine together and form a mean, and then you go on to output. But if you have max pooling, you could see that if you have max pooling, well, no, it's fully connected too. Yeah, actually, yeah. I'm going to scratch that thought. I have to refer my text. But I do think that a convolutional network with pooling layers still counts as fully connected. Yeah, I'm pretty sure it does. Okay, sorry about that. Converting from a lower feature, it's converting from a lower number of features, smaller matrix to a larger matrix. This is known as upsampling, another term that you see a lot in literature. Basically, it's self-referential. You're simply taking a lower amount of data, a smaller amount of data, and increasing it to a larger amount of data. And this simply, I mean, you simply do this to increase the resolution for feature maps. You do this all the time in, like, I mean, I don't know if any of you use Photoshop on a regular basis, but this is a pretty common function to make your images higher resolution. Other than segmentation, there are many other types of image classification tasks. There are denoising. Basically, you have a noisy image and you want to clean it up. You want to make it clearer. Image super resolution. Again, that sort of follows closely with upsampling, just improving the resolution of the image. Semantic segmentation, which this example is, and object detection, which simply involves finding where a particular object is. So for instance, if we want to know where the cars in the image are, that is a object detection problem. And typically the way that people handle object detection problems is that they simply train a model to output what's called a bounding box. What is simply a point and what is simply a origin point and a width times height of a box that is overlaid over the image that basically outlines where a particular object is. So bounding box problems are also very, very common in vision. Okay, all that makes sense? Yeah. Okay, so as far as image processing, as far as machine learning tasks go, you know, really a lot of machine learning comes down to how good your data set is. There's really no way to build a good model, a good generalizable model with a data set that is tiny or a data set that is of poor quality. But if you have a mediocre data set, if you have something that maybe isn't as large as you want, you know, there are ways to make it go further. Okay, so there are ways to simply improve what's called model generalization. So again, as we showed, I think in one of the previous lectures, if your data set is small and you keep training the network on a particular set of data, what happens? It becomes overtrained, right? It learns to become really, really good at identifying those pieces of data. And so that's a bad thing because presumably the whole point of a machine learning model is to be able to ship it to other people in order to be able to take it and have it work in the real world, right? So have it work in the real world on data that you haven't seen before. And if the model is simply learning to only be good at identifying the training data, then that's a problem, right? It sort of negates the whole point of machine learning. So this is what motivates basically the training sets, the whole division between training, validation, and test sets. You need a training set because you need to train the model, but you don't want that to be the judge of how well the model performs. So you keep a bit of data for yourself. That's your validation set, just to give yourself an idea of how well your model is doing on sort of a general piece of data that it hasn't seen before. And then you have a test set, which not even you see, which is used to compare your model with other people's, right? In competitions or something like that. So your training set could be huge. MNIST is pretty large, 70, 80K examples. That's awesome. Or it could be pretty small. A lot of data sets aren't more than 1,000 to 10,000 points. Okay, that's just, you know, most data sets are basically hand curated, and you know it's really expensive and tedious process to hand label an entire data set. I mean, I've been through the process. Many of you will probably encounter that process sometime in your life. So we need to make our data go as far as possible. And how do we do that? Well, maybe there's a way to artificially modify. The idea is there might be a way to artificially modify the data so that it's subtly different, But when the model sees it, it still has to label it as the same thing. So for instance, let's say we had an image. Okay. Let's say we had an image of a parrot, right? The model is being trained to identify parrots. Okay, so we have this one image of a parrot looking majestic, which is great, but we can't train the model on this one parrot 100,000 times. So we need other images of parrots. Now, barring us actually going to the Amazon and like taking a bunch of photos ourselves, there are things that we can do to make some new images from the old one that are similar but are still different enough. Okay, they're different enough to the model so that it won't only learn that parrots are perfectly framed inside this box and always sit on a branch and stuff. It will learn other features of what a parrot is. So for instance, we could crop the image so that whereas before we see the parrot's full body and feet, now we only see the parrot's face. So if we do this now on this image, instead of looking at the model, looking and seeing a branch or the feet, identifying that, oh, this is a parrot because it has a certain type of foot shape, now we'll have to see this image and sort of have to learn that, okay, parrots have this sort of beak shape. That becomes a thing. That becomes a new feature that some particular convolutional filter will identify. You could flip the image horizontally. Again, parrots don't always have to face the left. They could face the right. So that will make the image slightly different. You could blur the image. You can make the image a larger contrast. You could change the saturation or even the colors. I mean, parrots have all sorts of different plumages. And you could change the gamma value. You could change the gamma value to get all sorts of different images, right? So from this one image, you could get, 10 or maybe 20 more images. And if you do this and you send this to the model, it turns out that this actually does help. This does actually help the model train to get better at identifying parrots. And more importantly, it stops the model from overtraining, because that's the real hazard that you have with small data sets. You have such a small amount of data, you don't want the model to basically infer too much. You don't want the model, if you only had this one picture, the model could very easily assume, okay, parrots always have this green foliage in the background. That's always what a parrot is. But that's not true. That's not really relevant. So that's why being close up or changing the colors, those things subtly matter. Machine learning, the whole idea behind machine learning is that the computer wants to be as lazy as possible. It doesn't want to actually learn anything. It's like the worst college student you can imagine. It's just trying to get as low a loss as possible and call it a day. And so part of your job is to make sure that, yes, it is learning, it is getting a lower loss, but it's also learning the right things. So it's a little bit of give and take there. So these are what are called image augmentations. Basically, you have just a set of things that you can do. There are just certain things that you can do to go from a single image to multiple images that are the same image, but just subtly changed in a way. And hopefully the model will see those changes and realize that, okay, I need to look for the parrot's beak instead of looking for the parrot's feet. I shouldn't care about which way a parrot is facing. It could face left or right, and so on and so forth. Okay, make sense? Oh yeah, please don't.
Can you do like a random flip lambda color adjustment on the same?
Oh yeah, yeah. So you could do multiple of these transformations on the same image, and you could do it yourself. I mean, by all means, if you want to like it's not too hard in PyTorch. I grew up with like C++ and basically reading memory and manipulating memory and data, especially with like PNGs and JPEGs, which weren't bitmaps. That was a whole thing. But PyTorch makes that super easy. So you could do a lot of these transformations yourself, but PyTorch has this neat little, PyTorch and basically Torch Vision have all these nice little helper functions that allow you to make all these transformations. And I think they have a couple functions that basically do combinations of these transformations for you, just randomly for you. Be careful. all I could say is that please, for the love of God, if you use Torch Vision to make all these transformations, please just look at the data set once you're done with doing it, because you will not believe how many people I've seen that do these transformations and then just feed it straight into the model without looking to see what came out. And it's very easy to do a whole bunch of transformations and end up with images that look like nothing afterwards. Look at your data. That's the most important thing I could say. This is the most important advice I could give you. Look at your freaking data. Look at what your model is actually outputting. Yes, the loss graph is important, but it's not the whole thing in machine learning. Okay, make sense? All right. Other aspects, I'm sure you guys have seen this. A dropout is another way to prevent a model from overfitting. So again, we have a model. This is a fully connected model, and it will try to find certain features and match on certain features and train itself to identify every possible little nuance in an image to make its job easier. So again, with the parrot, I'm sure that there is part of it that would look to see for green foliage. It would look at those pictures, and if all our pictures with parrots had green foliage in them, there is part of the model that would sort of come to the conclusion, parrots clearly have to be surrounded by leaves. That's not necessarily true. I mean, you can imagine a parrot at a pet store or something. That's not true. Real world case where that assumption will fall apart. But that's sort of what the model wants to do. It's just trying to find little features that it could cheat to lower the loss as much as possible. So a way to stop it from doing that is to break some of these connections. Okay? If you're becoming too good at sort of identifying every little trivial detail, then maybe I could hack off part of your brain, and so you stop being able to look at every single detail, and you're going to focus more on the big details that matter. So that's the idea behind dropout. The dropout is simply meaning that if a model is, the idea behind dropout is simply that if a model is overfitting, then the assumption is the model has more capacity, it has more ability, it has more capacity, more memory than there are important features in the image. Okay? So what we do is just sort of break up the model's capacity. We just sort of, while we're training, this is important, while we're training, we just simply omit some of these weights. We get rid of some of these weights, some of these outputs, just break them, and then train the model like normal. Okay? So doing this actually does negate a big, doing this actually helps the model, it stops the model from overfitting, because again, it's working with less. So because it's working with less, it has to concentrate on only those features that matter. Only the big features, like what the beak, or like if the bird in the picture has a beak, if there's a wing, if there's a branch. It has to focus on that. It can't focus on, oh, is this particular color present in the picture or not. So that's the idea behind overfitting. I want to make sure, oh, there, okay, I'm going to bring, there is, oh, please.
With dropout, just like practically speaking, are you like actually manually going in and selecting like nodes to like remove, or is there more of an algorithm?
Oh, so good question. So with dropout, are you actually manually going in? And so for the longest time, the answer was yes, especially if you were using like sort of a basic CUDA or C++. You would just use sort of a random permutation, and then you would just sort of get a mask of value. You have a number of parameters. You would calculate sort of a vector of randomness, set a threshold, and then those values you would just tell your algorithm, don't update those values, right? That's just the idea behind dropout. But right now, PyTorch lets you do it automatically, so no one does it manually. But yeah, it did pretty much do manually also. You had to do it manually back in the day, but thank God for PyTorch. And you could set the dropout rate also. So you could set between 1% of the values could be dropped or 10%. Probably, I haven't seen anyone ever go above. I've seen 20%. I haven't seen anyone go above 20% though. It's very rare. It's usually on the single digits percentage. Yeah. Okay, so other thing, batch normalization. Again, so okay, so we need nonlinear activation functions. Why do we need nonlinear activation functions between each layer? Yeah, please.
If it's all linear, then the final neural network is just a future linear function.
Exactly. If we don't have those nonlinear activation functions between each layer, then the layers could simply combine together to just make one massive linear layer. And that doesn't really help us. I mean, for very simple problems, a simple linear network is useful. But other than that, we need some nonlinearity, right? So that's good. So that's good. The only slight problem is that, especially if it's with certain activation functions, the introduction of these nonlinearities could introduce weird distributions. So I'm talking basically Boltzmann-like distributions, where you have a very strong center around 0, and then you have a very long tail. So in those cases, generally, you don't want that. Generally, those types of distributions that have very long tails, that have lots of outliers, maybe that are bimodal, generally, it does bad things to the network. It's not huge. Well, it depends on the network. But generally, you want every layer to have sort of a Gaussian distribution of weights. Okay? So that's what you want. You don't necessarily get that always. So what you could do is simply normalize the layers, normalize the outputs at each layer so that they follow the particular standard normal curve. And that's what batch normalization is. All it is that if you have a particular feature map, height times width times number of channels, whatever, then you calculate the mean of the feature map, you calculate the standard deviation of the feature map. And so what you take, basically all you're doing, this term right here, is simply converting the feature. Instead of having a feature that's, say, 100, you are simply calculating how many standard deviations away from a mean that feature is, right? So that's, you're normalizing it, right? So instead of an absolute grade, for instance, you guys have, so for instance, in a lot of your classes, you have absolute grades that are terrible, right, in the 30s. Real kick in the head when you get that, right? But if the average is 10 and then the standard deviation is like 2 points, then you're sitting pretty, right, if you get a 30. So same idea here. We want to basically compress in a certain degree. We want to just renormalize each of the variables to say, for instance, if there is if the average is, let's say, 100, and then there's one variable that is 1,000, but the standard deviation is also 500, then we don't necessarily want that huge range of values. It'll just mess with our calculations. It's easier to just simply say, okay, that variable is simply 2 standard deviations away from the mean. That variable is simply 3. Okay? Or 2, sorry. That's the variable is simply 2. So that's what all batch normalization is. It's just simply normalizing the data to be normalizing the data to a more consistent scale. And it's easier for and it's easier just for on a computer from a computational perspective. Computers in general don't like to work with big numbers. They like to work with small numbers. Most of you are computer engineers. You know, I mean, you could probably tell why that is from your computer architecture courses. And everything just works out much better that way. So the batch normalization function is simply the actual value, the feature value, minus the mean, divided by the standard deviation. This will give you the number of standard deviations away from the mean a particular value is. Then we have two fitting parameters, gamma and beta, which beta just sets the new mean. Instead of having a mean of 0, this will give you always a mean of 0. Maybe you want a mean, some different mean. You could allow the model to pick a new mean and the deviation gamma. Again, standard deviation gamma, which the model will pick itself. Okay? So just renormalizes the data and makes things slightly easier to calculate. Make sense? Nice little trick. Sometimes it works, sometimes I don't think it's ever a negative. There are lots of times it doesn't necessarily work, but I don't think I've ever seen a time when this actually broke a network. Okay, so major thing. So with dropout, typically with dropout, you want to do dropout only during training, right? You want the model to be slightly stupid during training so it doesn't overfit. But you don't want, like during evaluation, during when you calculate the actual validation accuracy, the test accuracy, you don't want the model to still be stupid, right? You want it to use all its neurons it has available. So this is why PyTorch gives us a training mode and an evaluation mode. If we do model that's train, this turns on training mode. This means that when you go to train the model, dropout is activated, batch normalization is activated, et cetera, et cetera. When you go to turn on, and then when you say my model that evaluation mode, then dropout is disabled. Basically, when you put the image through the model, you use all the neurons now to get the answer. Same thing with batch normalization. Same thing with a lot of other modes that you could selectively that you use with PyTorch. So that's a neat little trick, I think. One of the better things with PyTorch is that it's its ability to basically allow you to simply switch between training mode and evaluation mode. Essentially, this is simply to turn dropout and batch normalization and other training tricks on and off. Make sense? Okay, so a bit of neural network history, and really this is convolutional neural network history because fully connected linear networks have existed for many decades. It's only in the last 20 years that machine learning has become popular, mainly because of convolutional neural networks, mainly because of GPUs, because convolutional neural networks are amazing, but the downside is you need a ton of computing power. They have a ton of features, right? So you need a lot of computing power in order to train them. So, 30 years ago, that wasn't really possible to do on a standard CPU. It would be too slow. But then we get GPUs. We get basically large processors that are that can perform thousands or tens of thousands, 100,000 calculations in parallel. So that's what allowed convolutional networks to be trainable, and that's what allowed us to finally be able to, that's finally what allowed machine learning and AI to explode, right? The first class to generally benefit from CNNs was image classification. And we've seen in image classification multiple times. Effectively, we get an image and we want to know if that image is a cat or a dog or a horse or a truck or whatever else. So some of the important events with image classification. I forgot that this was before 2000, but LeNet was published in 1998, which was simply a a very small convolutional network developed by l16 at Bell Laboratories. I don't think Bell Laboratories exists anymore, right? Or if it does, it's a shadow of what it used to be. But this was actually this was used for the handwriting digit classification, the MNIST data set. So one of the reasons why MNIST is so popular, like we use it all the time, is because the MNIST was one of the first data sets that was successfully classified using convolutional neural networks. And the convolutional neural network l16 showed it was actually very, very small. 28 by 28 image, 5 by 5 convolutions, 2 by 2 average pooling, another convolution, another pool, and then a couple linear layers, and that's basically it. But it works really well on the MNIST data set. So that was a huge success. Then the ImageNet data sets. Then after that, so the MNIST data sets had images of, so we know what the MNIST data set is, right? It's 10 categories of images. Just each category has 8,000, yeah. 8,000 handwritten samples of a particular digit. So that's awesome. And that's a huge boon. Thank God for the National Institute of Standards and Technology for creating that data set. It really helps prop up machine learning. But that it gets old. That data set is simple, and it could get old eventually. So in 2009, Fei-Fei Li and a whole bunch of co-authors started the creation of ImageNet data set classification. So this one, so here they just simply wanted a large image classification data sets, and this one took years and was hand labeled. And that is what's nuts about this data set, is that this isn't even 2 decades ago. This is like 15 years ago, that if you wanted a good data set, you had to hand label it. And so Fei-Fei Li could organize a huge effort to hand label, I think, tens of thousands of images. Hand label tens of thousands of images, and then host a image image recognition challenge every year to see who could classify these images well. And this thing has been, this has been ongoing. I think ImageNet is still ongoing. It has a ton of images now, over 1.2 million, 1,000 classes, and it's readily available in this GitHub repository. But the creation of this ImageNet data set, and specifically this challenge, sort of motivated a lot of people to explore image classification. And then, of course, in 2012, only about 10 years ago, a little over 10 years ago, l16 is published, which was one of the, it wasn't the first. Prior to l16, there were entrants that used CNNs, but it wasn't too popular in the computer vision and machine learning community, mainly because, again, convolutional neural networks are hugely resource intensive. So there wasn't really a great way to train them. You just had to sort of do it one by one on your CPU. It took a long time. And so the genius of Alex Krzyzewski is that he figured out how to use GPUs to train a much larger network than was seen before. So he used convolutional neural networks, but was able to use GPUs to basically calculate each of these layers parallelly. So it gave him a huge boost. Again, it still took days, weeks to train these models. CUDA was still new at the time, so it wasn't, and GPUs didn't have tensor cores or anything like that. So it still took a long time, but at least the time was tractable. At least it took days and not months, years to do it. So by using a exceptionally large, by using a large, for the time, convolutional neural network, AlexNet was able to pretty much dominate the 2012 CVPR conference. By I think he got an accuracy of 80-ish%, which was substantially better than. Oh yeah, okay, so 84%, which was substantially better than anyone else had at the time. Yeah, this was a huge thing. This was a huge thing at the time. Then you have VGG. You have deeper convolutional neural network models. You know, you could always get deeper. And so if you look at this actual model, I mean, it's kind of nuts. In 2 short years, you go from AlexNet, which was pretty much like basically just a few 5x5, 3x3, 12x12 convolutions to just an insane amount. But VGG basically got an even better accuracy score. There we go. Yeah. Then you have ResNets. Oh. Then you have a new issue, which is that there is a issue with making the models ever larger, and specifically with making if you make a neural network, keep making it larger, keep making it deeper. The issue there becomes this issue of catastrophic forgetting. Basically, the input becomes so far from the output that a whole bunch of stuff happens intermediately, and then the model starts forgetting features from the input. It just keeps sort of, it's like a game of telephone, right? If you guys have played that in school. You just get the image, and then you get some features from the image, and you get some more features, and you get more features. But if you do this too much, you sort of forget the original image. So not good. So GPs allowed us to make bigger models, but then we realized the deeper, like if there's a point where the model gets so deep that it basically becomes worse, and so what do you do in this case? You simply, Well, ResNet researchers came up with what's known as a skip connection. This is one of the early forms of detention. Basically, you have a bunch of feed-forward weight layers, but also you get the original input, and you let it skip a couple layers. Okay? So again, a big step up for machine learning models is this idea of attention, which we're going to discuss later this semester. But the use of these skip layers allows us to make dramatically deeper layers because, again, basically the image doesn't have to go through every single layer. It could skip a bunch of layers and go and just get added to the feature set. So it's this forgetting problem is effectively negated if you do this thing wisely. So that's where we're at. That's where we're at, which is that you want the image, and you want to know aspects of the image. You want to basically get features of the image, but you also want to retain your original image. So all this is doing is basically you're taking in an image, you're taking in parts of the image, you're calculating features from those parts, you're looking at the new parts of the image, you're calculating new features, and so on. Okay? So you do this. Basically, this creates a deep network. But there's another way to look at this. And the way to look at this is basically time. The way to look at this is that you're first taking a small part of the image, you're calculating based off that, then you're looking at a new part of the image, you're calculating based off that, then you're looking at a new part of the image, you're calculating based off that, and slowly you calculate new features, and then you process the image bit by bit, and you combine that over time, over depth. Okay? So that's what motivates the next part of what we're going to talk about, which is recurrent neural networks. Yeah, Dalvin.
What do those dotted skip lines mean in respect to, like you have a bunch of solid skip lines and the dotted
Oh.
would happen, like where you transition input between?
I honestly don't remember. I would have to look at the paper again. This is taken directly from a paper. I don't remember completely what the
Seems
done.
like, I don't know, maybe you can't skip those because you're changing input size at those skips.
Maybe, maybe. I'm hesitant to say. I don't want to say the wrong thing. Yeah, Patrick? Yeah.
The dotted skip lines use convolution with the kernel size of 1 because you can't just add a channel size of 256 to 512, for example. So a kernel size of 1 is basically a linear projection. It's not trying to recognize a new feature. So in that sense, it is kind of adding the original input to the next layer, which has a larger amount of channels.
All right, thank you. Wow, thank you, Patrick. Did you read the paper or?
I think so.
Oh, really? Oh, okay. I don't remember that at all, but okay, good. Okay, yeah. So the idea, you get ever deeper networks. The idea is that you process inputs piece by piece. You go process inputs and hidden layers concurrently. This brings you to the idea. This brings you to pretty much the idea of recurrent neural networks. So in the deep net architectures we've explored for both multi-layer perceptrons and convolutional neural networks, these are all referred to as feed-forward networks. Basically, they have no memory. It's just, you have an input, and it's just one state getting passed to another, getting passed to another. A long chain of calculations. Okay? Now, here's the thing. So in life, you don't necessarily have all the information all at once. You don't necessarily know the size of the information immediately, right? You think of that. You think of a sentence, right? And with an image, you have a piece of information that's always, that you know as that the resolution is what? 28 by 28. Awesome. With a sentence, you don't know how many words in this sentence is. Could be 5 words in the sentence, could be 43, right? So you need a new type of network that basically could take in a input piece by piece and then process it over time, okay? Piece by piece. So that's the motivation behind recurrent neural networks, that effectively you have a network that is simply a memory state, right? A memory state, and that takes in a particular input. So the combination of this memory state and this input gives you a output, and it gives you a new memory state. That's all our RNN is in its simplest form. You have a sequence of data, and at every data points, at t minus 1, you have the memory state h minus 1. You calculate a new memory, h of t, and you calculate the output, y of t minus 1. Then you go to the next input. You have a next input, x of t. You calculate and a memory state, h of t. You calculate a new memory state, h of t minus 1, and you calculate a new output, y of t. Okay? So this model is computed. So this is a recurrent neural network. It's named recurrent because it's basically self-referential. Recurrence, right? I know everyone's favorite concept in computer science is recursion. So you get to enjoy it here also. So the most basic type of recurrent neural network There we go. Okay. There we go. The most basic type of recurrent neural network is, again, you have a hidden state, you have a input state. These get appended together, and then they get passed into 2 linear layers. One linear layer is used to create a new hidden state. The other linear layer gets passed to, softmax function, and then it's used to create an output. Okay. So this is the simplest type of RNN model. Input, output, hidden state. There are many other more complex RNN models, but let's stick with this one for a minute. Let's look at the simple PyTorch RNN model. Let's look at an actual example. For instance, given the problem that you have a name and you want to understand the nationality that the name comes from. We want to categorize it according to what a nationality. So a nice little data set we have. We have a nice little data set, and we simply have the names from 19 nationalities. We have Arabic names, Nahas, Baz, Amari, sound very Arabic. We have Japanese names, Akimoto, Kira, Sakagami. We have Russian names, Babanov, Golovit, Salko. And each of these names sort of has a certain sort of quality, right? You see the TS a lot with Russian names. You see sort of names that end with with O or A or I with Japanese names. You see Nahas, Baz. You see a lot of Z's in Arabic names, those sorts of things, right? So we want to train the models to sort of identify the nationality of each of these names based off the name itself, okay? So what do we do? Well, first, we have to pass the name into the RNN. So how do we do that? Well, we would need to pass the data in sequentially. A name is simply a collection of characters, so we need to pass in one character at a time. Now, up until this point, the inputs have always been numbers, which is not, up until this point, the inputs have always been numbers. You know, with the images, each pixel is an actual RGB value. But that doesn't help us here because, you know, letters aren't numbers, right? So how do we pass in a letter into basically a numerical construct? Well, multiple different ways. We could embed each of the characters as a particular digit or embedding, or more common, we just embed the characters as what's known as a one-hot vector. In a one-hot vector, I'm sure you guys have seen this before, it's simply a vector of zeros, except for the place that corresponds to a particular character. So for instance, a one-hot vector if our alphabet was A, B, C, D, E, and the one-hot vector for A would be 1, 0, 0, 0, 0. The one-hot vector for E would be 0, 0, 0, 0, 1. Okay? Turns out one-hot vectors work fairly well. Yeah, one-hot vectors work very well. We'll get into other methods to embed. Into other methods to embed language or characters later in the semester. But this is basically the zeroth method. Okay. So we have a one-hot encoding strategy, which we could write a bit of code about. Credits to, what's his name? Oh man, I'm blanking on. Credit to Patrick Lober. There we go. Credit to Patrick Lober for making this example. He has a nice little YouTube channel that he teaches machine learning on. So thank you, credit to him. But basically, you have a bunch of utility functions that create one-hot vector based off a particular that create a one-hot vector for every character. Sorry. So, for instance, in the data sets that I mentioned, the characters are A through Z, both lowercase and uppercase, and a few punctuations. Especially like the apostrophes used a lot in African names or Middle Eastern names. So we need these few punctuations there. So we have 57 potential characters. So all we need to do. So for each letter, for instance, for the letter J, we create a one-hot vector and where it's all zeros except for the one which corresponds to that position J. Okay, and if we want to convert Jones to a vector, we simply have 5 one-hot vectors of size 57. Does that all make sense? So, doing all that, now that we could process the data, we could actually look at the code. We could actually code up the RNN. So we import our libraries, and we simply recall the RNN model that we're trying to implement. input hidden layer goes to linear layers, softmax output, and we write that in PyTorch. Again, we simply need to define a init function, and we need to define an init function. We have two linear layers corresponding to here, and then we have a softmax layer here. So we need to initialize these hidden layers, and then we need to know what the hidden size is. We could choose a hidden memory element of any size. And then we just calculate the forward network. We simply say the hidden, this is equal to the linear layer on the combined input and output, on the combined where the input tensor and the output tensor are concatenated. The output is simply equal to this linear layer on the combined and that goes through the softmax, and then you return the output and hidden values. And then we also need to have a different function to initialize the hidden layer here. Okay? So if we do all this, there we go. If we do all this, we could write this almost exactly the same code that we've written 100 times before. The training is simply we initialize the hidden state to be equal to zeros, and we simply calculate each of the output and hidden. We calculate the output and hidden for each character. Just run the RNN on each character, and then we calculate the loss on the last output. We take the last output, we calculate the loss against the ground truth, and then we do the zero gradient. We calculate the loss backward, and then we optimize, and then we use the optimizer to optimize the model. Okay? And so if we do that and we calculate the loss, we see that the loss goes from 3-ish, and it goes significantly down to 1.3. Okay, not the orders of magnitude decrease that we're used to, but again, these are names. Names don't fall neatly within any particular nationality. I think the model works pretty well, given that the input data is not, names aren't very clean in general. Make sense? Okay, so Then there are other types of recurrent neural networks that we could go through. But before we do, just remember that PyTorch, like most things, PyTorch has a built-in library for recurrent neural networks. So instead of actually programming the forward network like we did last time, we simply say, instead of programming in the two linear layers, the softmax layer, et cetera, we could simply say that the RNN, that we simply define a RNN layer. That's simply nn.rnn, input size, hidden layer size, number of layers, batch first. We'll get into what those mean, et cetera. And then the forward will simply be the input, so the input put through the RNN layer. Easy as that. And then the output could be anything. Again, the RNN gives you an output at every input step. So for certain situations, you might want the output at every input step, but for certain situations, maybe like the one like classification, like what we're doing right now, we only want the output at the last step. Output after the recurrent neural network gets every single character in the input. So for that, we simply take the last outputs and then pass it through our fully connected layer to get a logit that's given to the cross entropy function to calculate the loss. Make sense? So PyTorch is pretty nice. It saves us some effort there. Other aspects of other improvements you can make on the recurrent neural networks. First, spelling. Second, other aspects. So One of the problems with forward-only recurrent neural networks, as we designed before, is that not all information is present in prefixes, right? I mean, the way we talk, some of the information comes in at the end of the sentence instead of the first, and that could be especially relevant because sometimes an apple is an apple, and sometimes Apple is the company, right? And so the model needs to be able to distinguish between the two. But the only way to distinguish between the two is to get the information at the end of the sentence instead of at the beginning. So what do we do? So how do we improve a model in this case? Well, we use what's called a bidirectional RNN, not l16. To calculate the output, we simply have two RNNs running concurrently. And the first RNN gets the input from x0 to xn, same as before. The second RNN gets the input in reverse. It gets the input from xn to x0. Okay? So after you calculate the hidden states of both RNNs, basically you get the input from 0 to n, you get x0, you get the hidden state starts at 0, you get a new hidden state, this new hidden state goes here, you get x1, new hidden state that goes here, so on. You calculate the hidden states of the forward RNN, you calculate the hidden state of the backward RNN. Then once you have the hidden states of both RNN at every point of the input, you then pass them both to a feed forward network that'll let you get the output. Okay, so that's the idea behind a bidirectional RNN. Basically, you run a recurrent neural network forward, and you run a neural network backward, and then you combine the outputs of those two recurrent neural networks into a set of outputs. Okay? And then, for instance, if you wanted to classify, you could, for instance, take the first output and the last output, and then send those to a classification, or do something different. It doesn't matter. Depends on the problem. But the idea is that you could do that. The idea is that you can make an RNN, you could run it forward, you could run it backward, you could run it both ways, and in general, it performs better than if you simply ran it one way. And the nice thing is that, yes, this makes the calculation more complex, especially if you had to do it by hand or like in NumPy. But thanks to Torch, we have given Torch the nn.rnn module has a little bidirectional option that you can set to true to make the recurrent neural network bidirectional. Stacked RNNs, similar idea. Well, stacked RNNs are simply the same idea as stacked feed-forward networks. Maybe having more layers allows you to get more complex nonlinear functions, right? So, for instance, in this case, you have a single RNN that's calculated as normal. Then the output gets fed into another RNN that's calculated as normal. Same idea as a multi-layer network. I mean, it just works better because it allows you to get more. It allows you to fit the data in a more complex. It allows you to fit more complex data. So again, a bit harder to calculate, but thanks to PyTorch, you could set the number of layers. It defaults to 1, but you could set 2, 3, 100 layers, and it'll be able to create a stacked RNN structure. Okay, so one of the issues with RNNs is that, especially for long inputs, the further it has this issue of forgetting. Basically, you keep running the RNN, and then the further it gets from the beginning of the input, the less likely it is to remember features from the beginning of the input. It only has one hidden state. So, it keeps recalculating a hidden state based off the current input, and things get lost. It's like human beings. You keep doing stuff, The stuff that you did at the very beginning of your project gets forgotten compared to the stuff that you did right now. So, to avoid this problem, other RNN structures have been proposed. The most popular of which is the long short-term memory. The idea behind this structure is simply that you could have multiple gates to multiple hidden states. You have a hidden state and you have a cell state. The cell state is the memory. The hidden state the cell state is basically like a module memory. The hidden state is basically a module thought process, feature mapping. Okay? And so what you have here is that you could have multiple options to forget or add data to the cell memory. So what you do here is that you combine the X and H inputs, and you have what's called a forget gate. Or over here you have the cell memory. This is passed through this is multiplied by the sigma function of x1 times h times the respective weight parameter. So what do we know about sigma? We know sigma goes between 0 and 1. So because sigma is between 0 and 1, there is to be some values 0, there will be some values 1, right? So this gate right here is going to tell the cell those values that it's going to set certain values to 0 and tell the cell, just forget that data. We have another gate that is simply called the input gate. This new gate takes in the hidden state and the input and adds it to the cell memory. Okay, adds a portion of the input and hidden state to the cell memory. So basically, at so we first forget some part of our memory, then we add to some parts of our memory, and then finally we calculate the a new hidden state. That's called the output gate. So this is the idea behind a long short-term memory. You have some long memories that persist over multiple cycles. You have some short-term memories that get added and get forgotten at every possible time step. Okay, so a little bit of a complex function, but it works pretty well. And as you probably guessed, PyTorch allows you to implement an LSTM fairly simply, just simply using the nn.lstm file, nn.lstm file. And I included links all throughout this lecture, so you can look at some very good tutorials all over the internet. One last RNN before I let you go is called the gated recurrent neural network, gated recurrent unit. It looks simpler than LSTM, but it actually came after. And so the issue with the LSTM that people had was that it was complex. So, I forgot the authors of this paper. I forgot the authors that made the GRU. I'll remember eventually. But the idea was to simply make a simpler LSTM. So the good thing about a GRU is simply that you could get the same performance of an LSTM except without that cell hidden state. Without that cell hidden state, instead of a cell memory, you have what's known as a candidate activation vector, which acts a lot like a memory, but is actually just a new layer that gets values from the hidden layer and then produces a new memory based off that. So again, GRU, very popular, and it works as well as LSTM, sometimes better. And again, with PyTorch, it's very easy to implement for whatever function. You simply replace LSTM with GRU, all that's that. And then there is I highly recommend, there's a very famous blog post called The Unreasonable Effectiveness of RNNs. And it talks about how pretty much every different machine learning problem can be constructed, can be solved using a RNN architecture. So this is a picture from that blog post, and it just simply describes there are some problems that have a single input and a single output. This is like image classification. So you get a single image in, you get a single classification output. There are certain problems that have many input to one output. This is like sentiment classification. You get an Amazon review and you want to know if it's positive or negative. There are many problems that are basically many input and many output. So this is like text, this is like translation, part of speech tagging, that sort of thing, many to many. So all these problems could be handled by recurrent neural networks, which is why they're so important. Okay, all right. Long lecture, but that's all I have to do for today. I included a lot of links inside this Jupyter notebook, so feel free to go through it and go through all the like little blog posts and references that I included, because I try to only include the ones that I really like. All right, have a good day, guys. I'll see you Thursday.